Hey fellow nerds! Today we will learn how to analyze LTI systems using Z Transform. We will be covering transfer function, causality of LTI systems, stability of LTI systems, and analysis of LTI systems characterized by difference equations. Let us start by having a recap of what we have already learned. In the time domain, this is how we defined an LTI system. X of n is the input, y of n is the output, h of n is the impulse response. Here y of n will be the convolution of x of n and h of n. In the z domain, we take x of z as input. It is the z transform of x of n. The output y of z is the z transform of y of n. Also, h of z is the z transform of h of n. Here we have the relation y of z is the product of x of z and h of z. Let us take the input x of n to be equal to z raised to n. Then the output y of n is going to be the convolution of h of n and x of n. So it will be summation from k equals minus infinity to infinity, x of k, h of n minus k. But we know order doesn't matter in convolution, so we can also write summation from k equals minus infinity to infinity, h of k, x of n minus k. Here x of n is z raised to n, so x of n minus k will be z raised to n minus k. So we get summation from k equals minus infinity to infinity, h of k, z raised to n minus k. Z raised to n minus k can be split and written as z raised to n multiplied by z raised to minus k. Let us do that. The summation is with respect to the variable k, so z raised to n can come out of the summation. We know it doesn't matter what we call the variable to which we are giving the limit, so for more clarity, let us call it n. Now what I have over here is basically just the z transform of h of n, that is h of z. So the output y of n is simply z raised to n multiplied by h of z. When we gave the input as z raised to n, we got the output as z raised to n itself multiplied by h of z. But we have already learned that a signal for which the system's output is a constant multiplied by the input itself is called the eigenfunction of the system. So here z raised to n will be the eigenfunction of this LTI system. We have also learned that the amplitude factor is called the eigenvalue. Here z raised to n is multiplied by h of z. H of z is the amplitude factor. So h of z will be the eigenvalue of this LTI system. We know h of z is the z transform of the impulse function h of n. So we can write h of z is summation from n equals minus infinity to infinity h of n z raised to minus n. This is called the system function or the transfer function of the LTI system. We know z is taken as r e raised to j omega. So when we take r equal to 1, it represents the unit circle, that is z is equal to e raised to j omega. So if the ROC of our h of z actually includes the unit circle, then we can take r equal to 1 where z becomes e raised to j omega. In that case, h of z becomes summation from n equals minus infinity to infinity h of n. Z is e raised to j omega. E raised to j omega to the power n will be e raised to j omega n. But this is actually the expression for Fourier transform of h of n. So we can write if ROC of h of z includes the unit circle, then for z equal to e raised to j omega, h of z converges to h of e raised to j omega. That is, the z transform will be equal to the Fourier transform. Here h of e raised to j omega is the frequency response of the impulse function h of n. We already have a name for it. It is called the frequency response. Let us now learn how to check the causality of an LTI system using Z transform. Let us start by defining what a causal system is. An LTI system is supposed to be causal if its output only depends on the present and past values of the input. It should not depend on any of the future inputs. We have also learned that the impulse response of a causal discrete time LTI system should satisfy the condition h of n is equal to 0 for all n that is less than 0. But if h of n is equal to 0 for all values of n that is less than 0, then that means h of n is a right-sided sequence. And we have learned for a right-sided sequence, ROC of h of z is always going to be outside a circle in the z-plane. An important thing to note here is, even though I said it is going to be outside the circle in the z-plane, ROC may extend all the way into and possibly even include the origin. For example, let us take h of n to be the impulse sequence delta of n. We have learned the Z transform of delta of n. It is 1. For every value of Z, it is 1. So Z is allowed to take any value. So the ROC is the entire Z plane. Here it is not outside any circle. Instead, it is everywhere on the Z plane. Another important point here is, for a causal system, h of z is given by summation from n equal to 0 to infinity h of n z raised to minus n. Because h of n is 0 for every value of n that is less than 0. So we don't have to take the summation from minus infinity. We'll just take it from 0. Which means the value of n is always positive or 0. Which means the power of z, which is minus n, is always negative. Power of z never becomes positive, which means magnitude of z equal to infinity is always included in the ROC. When z becomes infinity, we'll get infinity to the power something negative. So it is going to be 0. So we can make the conclusion that a discrete time system is causal if and only if the ROC of its system function is the exterior of a circle, including infinity. We have also learned from the property 8 of ROC that if h of z is rational, then ROC must be outside the outermost pole and it must include infinity. If the ROC of h of z includes infinity, that means limit z tends to infinity h of z must be a finite value. It should converge to a finite value. It should not be infinite. But that implies that the degree of numerator of h of z should not be greater than the degree of the denominator of h of z. Why? Let us take an example to understand that. Assume h of z is z cube plus 1 divided by z square. I want to find limit z tends to infinity h of z. I'll divide the numerator and the denominator with z square. Then I will get limit z tends to infinity z plus 1 by z square divided by 1. If I give z equal to infinity, 1 by z square will become 0, but still I have a z. So this will become infinity. When the degree of the numerator is greater than the degree of the denominator, limit z tends to infinity h of z is not finite, it is infinite. Let us take another example. My h of z is z square divided by z cube plus 1. Here the order of the numerator is less than the order of the denominator. If I give limit z tends to infinity, I will divide the numerator and the denominator with z square. Then I get limit z tends to infinity 1 by z plus 1 by z square. If I give z equal to infinity, 1 by z square becomes 0. Then I have 1 by z, that also becomes 0. So this is 0, which is a finite value. Let us take another case where the orders are the same. I'll take z square divided by z square plus 2. Let us apply the limit z tends to infinity. I am going to divide the numerator and the denominator with z square. I get limit z tends to infinity 1 by 1 plus 2 by z square. Now if I give z equal to infinity, 2 by z square becomes 0. So this is equal to 1, which is a finite value. Therefore, for limit z tends to infinity h of z to be finite, the degree of the numerator h of z should not be greater than the degree of the denominator. Degree of the numerator can be less than the degree of the denominator. The degree of the numerator can be equal to the degree of the denominator, but degree of numerator cannot be greater than the degree of the denominator. Let us make our conclusions from what we learned. A discrete time LTI system with rational function h of z is causal if and only if The ROC is the exterior of a circle outside the outermost pole. Also, with h of z expressed as a ratio of polynomials in z, the order of the numerator cannot be greater than the order of the denominator. Let us solve a problem based on this. We have to check the causality of an LTI system. Its a system function h of z is given. It is z cube minus 2z square plus z divided by z square plus 1 by 4z plus 1 by 8. Here h of z is written as a ratio of polynomials in z, and obviously the numerator of h of z is of higher order than the denominator. Order of the numerator is 3, order of the denominator is 2. So we can conclude the system is not causal. Let us solve another problem. We have to check the causality of an LTI system. Its system function h of z is given 1 by 1 minus 1 by 2 z inverse plus 1 by 1 minus 2 z inverse. ROC is magnitude of z is greater than 2. Obviously, h of z has two poles. One is at 1 by 2, the other is at 2. The outermost pole obviously is 2, and magnitude of z is greater than 2, which means ROC is the exterior of the circle outside the outermost pole. So we can conclude that h of n is a right-sided signal. H of z in the question is given as a summation of two terms. If we add both of them, this is what we get. 2 minus 5 by 2 z inverse divided by 1 minus 1 by 2 z inverse multiplied by 1 minus 2 z inverse. To see the degree of the numerator and the denominator properly, let us multiply the numerator and the denominator by z square. Now, z minus 1 by 2 multiplied by z minus 2 is z square minus 5 by 2 z plus 1. Let us replace it. Now we can see that the degree of the numerator is 2, degree of the denominator is also 2. So degree of the numerator and degree of the denominator are equal. Therefore, the system is causal. Now let us learn how to check the stability of an LTI system using Z transform. We have already learned that for a discrete time LTI system to be stable, the impulse response should be absolutely summable. But we have already learned if the impulse response is absolutely summable, then the Fourier transform converges to a finite value. But if the Fourier transform converges to a finite value, that means the ROC of h of z must include the unit circle. From this, we can make the conclusion that a discrete time LTI system is stable if and only if the ROC of its system function or the transfer function h of z includes the unit circle where magnitude of z is equal to 1. Let us solve a problem based on this. We have to check the stability of an LTI system. Its system function h of z is given as 1 by 1 minus 1 by 2 z inverse plus 1 by 1 minus 2 z inverse. This is the same system we discussed in the last problem. There are three cases. In the first case, ROC is magnitude of z being greater than 2. In the second case, it is between 1 by 2 and 2. In the third case, it is less than 1 by 2. Let us take the first one. Here magnitude of z is greater than 2. So obviously ROC does not include the unit circle where magnitude of z should be equal to 1. Therefore, the system is unstable. But ROC is the exterior of a circle that is outside the outermost pole. So h of n is right-sided and its ROC is the exterior of a circle including infinity. So the system is causal. Let us take the second case. Magnitude of z is between 1 by 2 and 2. So obviously ROC includes the unit circle where magnitude of z should be equal to 1. So we can say the system is stable. Here ROC is not the exterior of a circle outside the outermost pole. So we can say h of n is not right-sided. Therefore the system is not causal. In the third case, magnitude of z is less than 1 by 2. Which means ROC does not include the unit circle where magnitude of z is equal to 1. So we can conclude the system is unstable. Again, since ROC is not the exterior of a circle outside the outermost pole, we can say h of n is not right-sided and therefore the system is not causal. Another important thing we can note here is that a causal LTI system with a rational system function h of z is also stable if and only if all of the poles of h of z lie inside the unit circle. Or in other words, we can say all the poles must have a magnitude that is less than 1. Let me show you why by taking an example. We already know that for a causal LTI system, the ROC of the system function is the exterior of the circle outside the outermost pole. So, if there is any pole outside the unit circle, the ROC definitely will not contain the unit circle. But for the system to be stable, unit circle has to be included in the ROC. For example, let us take this one. Here we have a pole that is outside the unit circle. So obviously ROC only can be to the exterior of this circle and it will not include the unit circle. Let us take this case. Here all the poles are inside the unit circle. Therefore, when we take ROC to be the exterior of the circle that is outside the outermost pole, it is going to include the unit circle as well. So we can conclude this is the ROC of a stable system and this is the ROC of an unstable system. So for a causal LTI system with rational system function to be also stable, all of its poles should be inside the unit circle or they should all have magnitude less than 1. Let us solve a problem based on this. We have to check the stability of a causal LTI system whose system function is given. H of z is 1 by 1 minus 2r cos theta z inverse plus r square z raised to minus 2. Since it is already given that the system is causal, all we have to check is if the magnitude of the poles are less than 1 or not. If they are less than 1, the system will be stable. If they are not less than 1, then the system will not be stable. To find the poles, let us multiply the numerator and denominator with z square. Then we get h of z like this. We know poles are the roots of the denominator. So we have to find the root of this quadratic expression. Roots of a quadratic expression of the form ax square plus bx plus c is of the form minus b plus or minus root of b square minus 4ac divided by 2a. Using this, we can write the roots of the denominator of h of z. Minus b will be minus of minus 2r cos theta, that is 2r cos theta, plus or minus root of b square is 4r square cos square theta minus 4ac will become minus 4r square divided by 2a is 2. We have 4r square cos square theta minus 4r square. Let us take 4r square as common. Then this will become 4r square multiplied by cos square theta minus 1. Root of 4r square is 2r. Let us take it out of the root. Now we have cos square theta minus 1 under the root. Cos square theta minus 1 is the same as minus sin square theta. Root of sin square theta is sin theta. Let us take it out of the root. Now all we need is root of minus 1, which is j. Let us put j over here. We have 2 here, 2 here and 2 here. They all can be cancelled. So this becomes r cos theta plus or minus j r sin theta. Or we can write r multiplied by cos theta plus or minus j sin theta. Therefore, the two roots are r multiplied by cos theta plus j sin theta and r multiplied by cos theta minus j sin theta. So these two will be where the poles are. Cos theta plus j sin theta can be written as e raised to j theta. Cos theta minus j sin theta can be written as e raised to minus j theta. So we can say the poles are at r e raised to j theta and r e raised to minus j theta. We need the magnitude of the poles. Magnitude of r e raised to j theta will be equal to magnitude of r e raised to minus j theta and they will be equal to r because magnitude of e raised to j theta and magnitude of e raised to minus j theta are simply 1. So finally we can conclude that whether this system is stable or not depends on the value of r. The two poles are at r e raised to j theta and r e raised to minus j theta. That means they are both at a distance r from the origin. One of them makes the angle theta with the x-axis, the other makes the angle minus theta with the x-axis. If R is less than 1, the ROC will contain the unit circle and the system will be stable. If R is greater than 1, the ROC will not contain the unit circle and the system will be unstable. Let us now move on to analyzing LTI systems that are characterized by difference equations using Z transform. We will start by taking an LTI system with input x of n and output y of n. Let's write the general linear constant coefficient difference equation for the system. The general expression is summation from k equals 0 to n a k y of n minus k is equal to summation from k equals 0 to m b k x of n minus k. We have used this in discrete time Fourier transform also. Let us expand both sides of the equation. Then we get for k equal to 0, a0 y of n plus for k equal to 1, a1 y of n minus 1. K takes values up to n, so there will be n terms. The nth term will be an y of n minus n. This will be equal to, when you give k equal to 0, we get b0 x of n plus b1 x of n minus 1. K can take values up to m, so there will be m terms. The mth term will be bm x of n minus m. Now let's take the Z transform on both sides of the equation. A0 is a constant, so Z transform of A0 y of n is going to be A0 y of z. A1 is a constant, y of n minus 1 is a time shifted version of y of n. Shifting factor is 1, so its Z transform is going to be A1 multiplied by Z inverse y of z. This goes up to n terms. Z transform of the nth term is going to be an z raised to minus n y of z. Using the same way, we can write the right hand side also. It will be b0 x of z plus b1 z inverse x of z plus the mth term will be bm z raised to minus m x of z. On the left hand side, all the terms have y of z in it. On the right hand side, all the terms have x of z in it. So let us take them as common. Then we get y of z multiplied by a0 plus a1 z inverse plus up to an z raised to minus n is equal to x of z multiplied by b0 plus b1 z inverse plus up to bm z raised to minus m. From this, we can write y of z divided by x of z. It will be this divided by this. We can write the denominator and the numerator as a summation. So this becomes summation from k equals 0 to m bk z raised to minus k divided by summation from k equal to 0 to n ak z raised to minus k. But we have already learned that for an LTI system, y of z, that is the Z transform of the output, is the product of h of z and x of z. That means if you take y of z divided by x of z, that should be equal to the system function h of z. So what we have over here is nothing but h of z. Let us put it in a box. So we got for an LTI system that is characterized by difference equations, h of z is summation from k equals 0 to m bk z raised to minus k divided by summation from k equals 0 to n ak z raised to minus k. Here the numerator is b0 plus b1 z inverse plus b2 z raised to minus 2 etc. And the denominator is a0 plus a1 z inverse plus a2 z raised to minus 2 etc. Obviously, both of these are polynomials in z inverse. So h of z is the ratio of two polynomials, which means h of z is rational. So we can conclude for a system that is satisfying a linear constant coefficient difference equation, the system function is always going to be rational. Let us now solve a problem. It is given that the input and output of the LTI system satisfies this difference equation. Y of n minus half y of n minus 1 is equal to x of n plus 1 by 3 x of n minus 1. We have to find the impulse function if the system is anti-causal and unstable and when it is causal and stable. We have the difference equation here. So the first thing we are going to do is to take the Z transform on both sides. On the left hand side, we have y of n. Its Z transform is y of z. We have minus 1 by 2 y of n minus 1. Its Z transform is going to be minus 1 by 2 z inverse y of z. This is equal to Z transform of x of n is x of z. Z transform of 1 by 3 x of n minus 1 is 1 by 3 z raised to minus 1 x of z. On the left hand side, let us take y of z as common. Then it will be y of z multiplied by 1 minus 1 by 2 z inverse. On the right hand side, let us take x of z in common. Then we get x of z multiplied by 1 plus 1 by 3 z inverse. We know h of z is y of z by x of z. So here we get h of z to be 1 plus 1 by 3 z inverse divided by 1 minus 1 by 2 z inverse. Let us split this into two terms. We can write 1 by 1 minus 1 by 2 z inverse and 1 by 3 z inverse divided by 1 minus 1 by 2 z inverse. Obviously, h of z only has one pole and it is when 1 minus 1 by 2 z inverse becomes equal to 0. So we can write the pole is where magnitude of z is equal to 1 by 2. So we can write that the pole of h of z is where z is equal to 1 by 2. Since there is only one pole, there are two options for ROCs. Either magnitude of z can be less than 1 by 2 or it can be greater than 1 by 2. Let us take the first case where magnitude of z is less than 1 by 2. If magnitude of z is less than 1 by 2, that means the ROC of the system function is the interior of the circle inside the innermost pole. Here ROC is inside the circle, so h of n is left-sided. Therefore, the system is anti-causal. Also, magnitude of z is less than 1 by 2, so magnitude of z cannot be 1, which means the unit circle is not included. Therefore, the system is also unstable. So, we are dealing with an anti-causal and unstable system. Here h of n is left-sided, so let us try to find the inverse z transform for h of z that is given over here. Let us write h of n. The first term is 1 by 1 minus 1 by 2 z inverse. It is of the form 1 by 1 minus a z inverse. We already found h of n is left-sided, so its inverse is going to be minus a raised to n u of minus n minus 1. Here a is 1 by 2. So we get minus 1 by 2 to the power n u of minus n minus 1. The second term is 1 by 3 times z inverse 1 by 1 minus 1 by 2 z inverse. So first we can write plus 1 by 3. This is z inverse multiplied by something. Let us just take this part. We already found its inverse. It is minus 1 by 2 to the power n u of minus n minus 1. But what we have to find out is the inverse of z inverse multiplied by 1 minus 1 by 2 z inverse. Let us use the time shifting property. Z raised to minus n naught multiplied by x of z is the z transform of x of n minus n naught. Here we have z raised to minus 1, so n naught is 1. This is our x of z, so we can take this to be our x of n. This is z inverse multiplied by x of z. So its inverse is going to be x of n minus 1. Basically, every n over here will have to be changed into n minus 1. So we get minus 1 by 2 to the power n minus 1 u of minus n minus 1 minus 1. This becomes minus n plus 1 minus 1. Plus 1 and minus 1 gets cancelled. We simply get u of minus n. So inverse of Z inverse multiplied by 1 by 1 minus 1 by 2 Z inverse is minus 1 by 2 to the power n minus 1 u of minus 1. Let us add it over here. Now let's take the second case where magnitude of Z is greater than 1 by 2. Here ROC is outside the circle, so h of n is right-sided. Magnitude of Z can take any value greater than 1 by 2, so Z equal to infinity is also included in the ROC. Therefore, the system is causal. Magnitude of Z is greater than 1 by 2, which means unit circle is included, so the system is also stable. That means we are dealing with a causal and a stable system. Keeping in mind that h of n is right-sided, let us try to find the inverse of h of z given over here. H of n is going to be, the first term is 1 by 1 minus 1 by 2 z inverse. This is of the form 1 by 1 minus a z inverse. In case it is right-sided, its inverse is going to be of the form a raised to n u of n. Here a is 1 by 2, so we get 1 by 2 raised to the power n u of n. The second term is 1 by 3 z inverse 1 by 1 minus 1 by 2 z inverse. Let us write plus 1 by 3 first. We have z inverse multiplied by 1 by 1 minus 1 by 2 z inverse. We already know the inverse of this much. It is 1 by 2 raised to n u of n. So if we want the inverse of z inverse multiplied by that, using time shifting property, it will simply be x of n minus 1, or basically we just have to change all n's here into n minus 1. So we can write 1 by 2 raised to the power n minus 1 u of n minus 1. Therefore, if the system is anti-causal and unstable, this is the impulse function. If it is causal and stable, this is its impulse function. Let's solve another problem. We have to analyze a system. It is given that if the input is x1 of n, which is 1 by 6 raised to n u of n, then the output is y of n, which is a 1 by 2 raised to n 10 1 by 3 raised to n u of n. It is also given if the input is x2 of n, which is minus 1 raised to n, then the output is y2 of n, which is 7 by 4 minus 1 raised to n. Let us take the first part. x1 of n is 1 by 6 raised to n u of n. Let us write its Z transform, which is x1 of z. This is of the form a raised to n u of n. So its Z transform will be 1 by 1 minus 1 by 6 Z inverse, and ROC will be magnitude of Z being greater than 1 by 6. Output is a 1 by 2 raised to n u of n plus 10 1 by 3 raised to n u of n. So its Z transform y1 of Z is going to be a multiplied by 1 by 1 minus 1 by 2 Z inverse plus 10 multiplied by 1 by 1 minus 1 by 3 Z inverse. Let's put a on top of this and 10 on top of this. For this part, magnitude of Z should be greater than 1 by 2. For this part, it should be greater than 1 by 3. So ROC is going to be where magnitude of Z is greater than 1 by 2. But that is not what matters now. Let us add these two. If you do that, you will get a plus 10 minus 5 plus a by 3 Z inverse divided by 1 minus 1 by 2 Z inverse multiplied by 1 minus 1 by 3 Z inverse. We have x1 of z, we have y1 of z. So using this, we can find our system function. It is y1 of z divided by x1 of z. Y1 of z is over here, x1 of z is over here. If you take their ratio, this is what you get. Now consider the second part of the question. x2 of n is minus 1 raised to n, then y2 of n is a constant multiplied by minus 1 raised to n. We learned at the starting of this video, if the input is z raised to n, output is h of z, z raised to n. Let us take z is equal to minus 1. Then, if the input is minus 1 raised to n, then output should be h of minus 1 multiplied by minus 1 raised to n. Compare it with what we have here. Our input is minus 1 raised to n. Our output is something multiplied by minus 1 raised to n. Something should be h of minus 1. So h of minus 1 is 7 by 4. So from 2 we can write h of minus 1 is 7 by 4. H of z is over here. So if you substitute all z's by minus 1, we will get h of minus 1. It is a plus 10 plus 5 plus a by 3 multiplied by 7 by 6 divided by 3 by 2 multiplied by 4 by 3. All I have done is I took z is equal to minus 1. Now this is equal to 7 by 4. The only unknown in this equation is a. So if you solve this, you will get the value of a. A is actually minus 9. Let us put the value of a back in this equation so we get our actual h of z. A plus 10 becomes minus 9 plus 10, which is 1. 5 plus a by 3 will become 5 minus 9 by 3, 5 minus 3, that is 2. So this whole thing becomes 1 minus 2z inverse. So h of z is simply 1 minus 2z inverse multiplied by 1 minus 1 by 6 z inverse divided by 1 minus 1 by 2 z inverse multiplied by 1 minus 1 by 3 z inverse. So we found the transfer function of the system. It has two poles, one at 1 by 2 and the other at 1 by 3. So we have three options for ROC. Either it can be lesser than 1 by 3, or it can be between 1 by 3 and 1 by 2, or it can be greater than 1 by 2. To figure out which one we have to take, let's go back to y1 of z. It is written as two parts, and we know for the first part magnitude of z should be greater than 1 by 2. For the second part it should be greater than 1 by 3. So obviously since 1 by 3 is less than 1 by 2, its ROC will be where magnitude of z is greater than 1 by 2. So we can write ROC of y1 of z is magnitude of z being greater than 1 by 2. Now comes the trick. We know y of z is h of z multiplied by x of z. From the convolution property, we know its ROC should contain the intersection of the two ROCs of h of z and x of z. Here ROC of y of z is magnitude of z being greater than 1 by 2. ROC of x of z is magnitude of z being greater than 1 by 6. We have three options for ROC of h of z. One is magnitude of z being less than 1 by 3. The second one is where it is between 1 by 3 and 1 by 2. The third is when it is greater than 1 by 2. If we consider the first one, if ROC of h of z is magnitude of z less than 1 by 3, in that case ROC of y of z should be between 1 by 6 and 1 by 3, but it is greater than 1 by 2. So this is not the correct answer. Let's consider the second one. For x of z, it is greater than 1 by 6. For h of z, it is between 1 by 3 and 1 by 2. So the intersection is going to be between 1 by 3 and 1 by 2. But y of z has ROC greater than 1 by 2, which means this is also not the correct answer. Let's take the third one. For x of z, magnitude of z should be greater than 1 by 6. For h of z, it should be greater than 1 by 2. So their intersection will be greater than 1 by 2, which is exactly what we have over here. So the correct answer is magnitude of z is greater than 1 by 2. Let us write it down. ROC of h of z is magnitude of z being greater than 1 by 2. Since magnitude of z is greater than 1 by 2, ROC includes the unit circle, which means our system is stable. Now to check the causality, we have to check the order of the numerator and the denominator. For a better view, let us multiply the denominator and the numerator with z square. Then this becomes z minus 2 multiplied by z minus 1 by 6 divided by z minus 1 by 2 multiplied by z minus 1 by 3. Now z minus 2 multiplied by z minus 1 by 6 is z square minus 13 by 6 z plus 1 by 3. Also z minus 1 by 2 multiplied by z minus 1 by 3 is z square minus 5 by 6 z plus 1 by 6. We can see that the order of the numerator is 2, order of the denominator is also 2. So we can write h of z is a ratio of polynomials in z and the order of the numerator is not greater than that of the denominator, which means the system is causal. While we are at it, let's also write the difference equation that defines this system. For that, we need h of z. To make it easier for us, I am going to divide the numerator and the denominator by z square. Then this is what we get. Let's try to write the difference equation by inspection. We learned h of z can be written like this: summation from k equal to 0 to m bk z raised to minus k divided by summation from k equals 0 to n a k z raised to minus k. Expanding the summation, we can also write it like this. Comparing with what we have over here, we can see b0 is 1, b1 is minus 13 by 6, b2 is 1 by 3, a0 is 1, a1 is minus 5 by 6, a2 is 1 by 6. The general expression for difference equation is a0 y of n plus a1 y of n minus 1 plus up to n terms. This is equal to b0 x of n plus b1 x of n minus 2 up to m terms. Since we got all the coefficients, we can write the difference equation. On the left hand side, I will have y of n minus 5 by 6 y of n minus 1 plus 1 by 6 y of n minus 2. I got the coefficients of y of n minus 1 and y of n minus 2 from the denominator of h of z, 1 minus 5 by 6 and plus 1 by 6. This will be equal to x of n minus 13 by 6 x of n minus 1 plus 1 by 3 x of n minus 2. I got the coefficients of x of n minus 1 and x of n minus 2 from the numerator of h of z, 1 minus 13 by 6 and plus 1 by 3. Let us solve another problem. There is a system that is stable and causal. Its impulse response is h of n. Its system function is h of z. H of z is rational. It is given that h of z has a pole at z equal to 1 by 2. It also has a 0 somewhere on the unit circle. We have to determine whether Fourier transform of 1 by 2 raised to n h of n converges to a finite value. H of e raised to j omega is 0 for some value of omega. H of n has a finite duration. And whether g of n defined as n multiplied by convolution of h of n with h of n itself is the impulse response of a stable system. Let's start with the first one. We know h of z is given as summation from n equals minus infinity to infinity h of n z raised to minus n. Now consider magnitude of z is equal to 2. That means z is equal to 2 e raised to j omega. In that case, h of z will become summation from n equals minus infinity to infinity h of n 2 e raised to j omega raised to the power minus n. We have 2 e raised to j omega raised to the power minus n. We can write it like this: 2 raised to minus n e raised to minus j omega n. 2 raised to minus n can be written as 1 by 2 raised to the power n. Let's put 1 by 2 raised to n before h of n. Now we get summation from n equals minus infinity to infinity 1 by 2 raised to n h of n e raised to minus j omega n. But this is the expression to find the Fourier transform of 1 by 2 raised to n h of n. So to check whether Fourier transform of 1 by 2 raised to n h of n converges to a finite value, we have to check whether h of z converges to a finite value when magnitude of z is equal to 2. Which means we have to check whether magnitude of z being equal to 2 is in the ROC of h of z. It is given in the question that the system is stable and causal, which means all the poles should be inside the unit circle. Therefore, z equal to 2 will be included in the ROC, and that means h of z converges to a finite value when z equal to 2, and therefore Fourier transform of 1 by 2 raised to n h of n converges to a finite value. The statement is true. Let's take the next one. We have to check whether h of e raised to j omega is 0 for some value of omega. It is given in the question that there is a 0 on the unit circle. So for some value of omega, h of z is equal to 0 when magnitude of z is equal to 1. But z can be written as r e raised to j omega. So we can write h of r e raised to j omega is equal to 0 for some value of omega when magnitude of r e raised to j omega is equal to 1. But magnitude of e raised to j omega is already 1. So the condition here is r is equal to 1. If r is 1, here instead of r e raised to j omega, we can simply write e raised to j omega. Then we can see that the statement is correct. H of e raised to j omega is 0 for some value of omega when r is 1. Let's see the next one. We have to check whether h of n has finite duration. We know for a finite duration sequence, the entire z-plane is its ROC except possibly z equal to 0 and or z equal to infinity. But it is given in the question h of z has a pole at z equal to 1 by 2. So definitely the entire z-plane cannot be its ROC even if we exclude z equal to 0 and z equal to infinity. So the statement is false. Let's go to the next one. We have to check whether if g of n is defined as n multiplied by convolution of h of n with itself is the impulse response of a stable system. The system given in the question is causal. Therefore, its h of n will be 0 for all n that is less than 0. Therefore, if we take the convolution of h of n with h of n itself, it will also be 0 for all values of n that is less than 0. Again, if we multiply this with n, this is again going to be 0 for every value of n that is less than 0. Because when n is less than 0, convolution of h of n with itself is 0. So if you multiply it with n, the product is still going to be 0. This is what we are calling g of n. So we can write g of n is equal to 0 for n less than 0. Which means if there is a system whose impulse response is g of n, that system is going to be causal. Again, let us take the convolution of h of n with h of n. Z transform of h of n is h of z. Z transform of h of n is h of z. So the Z transform of the convolution is going to be h of z multiplied by h of z, that is h square of z. We have to find the Z transform of n multiplied by convolution of h of n with itself. We can use the differentiation property here. Z transform of n x of n is minus z d by dz of x of z. Here we have n multiplied by x of n being convolution of h of n and h of n. So the Z transform will be minus z multiplied by d by dz of h square of z. This is the Z transform of g of n. So let us call it g of z. But the most important part is ROC is still going to be R, which means h square of z and g of z will have the same ROC. Our original system is stable and causal, which means all of its poles will be inside the unit circle. So for g of z also, all the poles will be inside the unit circle, which means the new system is also stable. This statement is true. The next concept we have to learn is unilateral Z transform. Usually we write x of z is summation from n equals minus infinity to infinity x of n z raised to minus n. This is called bilateral Z transform. Instead of this, if we take x of z to be summation from n equals 0 to infinity x of n z raised to minus n, then this is called unilateral Z transform. In fact, initial value theorem and final value theorem are only applicable to unilateral Z transform. Unilateral Z transform is useful to analyze causal systems that are specified by linear constant coefficient difference equations with non-zero initial conditions. We will be notating it using a double-sided arrow with uz written on top of it. We know in bilateral Z transform, we take the summation from minus infinity to infinity. In unilateral, we take it from 0 to infinity. Now, let us take the bilateral Z transform of a signal x of n. It is summation from n equals minus infinity to infinity x of n z raised to minus n. Assume x of n is equal to 0 for all values of n that is less than 0. That means we don't have to take the summation from minus infinity, we can just take it from 0. So this is equal to summation from n equals 0 to infinity x of n z raised to minus n. But this is unilateral Z transform. So we can say if x of n is equal to 0 for all values of n that is less than 0, unilateral and bilateral Z transforms will be identical. Now let us take the bilateral Z transform of x of n multiplied by u of n. That is summation from n equals minus infinity to infinity x of n u of n z raised to minus n. But u of n is non-zero only for the values of n that is greater than or equal to 0. For every value of n that is less than 0, u of n is 0. So we don't have to take the summation from minus infinity. We can just take it from 0. So this will be equal to summation from n equals 0 to infinity x of n value of u of n for every value of n that is greater than or equal to 0 is 1. So we can just put multiplied by 1 z raised to minus n. What we got over here is the unilateral Z transform of x of n. What we started with is the bilateral Z transform of x of n u of n. So we can write unilateral Z transform of x of n can be thought of as bilateral Z transform of x of n multiplied by u of n. The most important conclusion we can make from here is this. X of n is multiplied by u of n. So it is going to be 0 for every value of n that is less than 0, and it is only going to be non-zero when n is greater than or equal to 0, which means x of n u of n is always right-sided. And we know for a right-sided sequence, ROC is always the exterior of a circle. So we can conclude ROC for unilateral Z transform is always the exterior of a circle. We got the expression for unilateral Z transform. Let us expand the summation. X of z is equal to, if you give n equal to 0, it is x of 0 z raised to 0, which is 1, plus if you give n equal to 1, x of 1 z raised to minus 1, plus if you give n equal to 2, x of 2 z raised to minus 2, it goes like that up to infinite terms. Here, n can only take values that are greater than 0, which means the power of z, which is minus n, is always going to be negative. In unilateral Z transform, n should always be greater than or equal to 0. That means in the power series expansion, z cannot have a positive power. And as a consequence of this, when x of z is written as a ratio of polynomials p of z by q of z, order of the numerator will always be less than or equal to order of the denominator. Let me explain the reason. Assume that the numerator has higher power. Then if you do the long division, the answer will have positive powers of z in it. For example, z cube divided by z square. This will give you z which has a positive power. But z square by z cube will give you z raised to minus 1, where z has a negative power. If you take z cube divided by z cube, this is 1 or z raised to 0. Here the power is 0, which is also acceptable. So order of the numerator should always be less than or equal to the order of the denominator. Let us solve a problem. Unilateral Z transform of a sequence x of n is given. x of z is 3 minus 5 by 6 z inverse divided by 1 minus 1 by 4 z inverse multiplied by 1 minus 1 by 3 z inverse. We have to find the sequence x of n. The first thing we have to do is use partial fraction expansion to write x of z in this form. A by 1 minus 1 by 4 z inverse plus b by 1 minus 1 by 3 z inverse. We have to find a and b. A will be equal to limit z tends to the pole corresponding to a, which is 1 by 4 here. So z tends to 1 by 4. 1 minus 1 by 4 z inverse, which is the denominator, multiplied by x of z. That is limit z tends to 1 by 4. We have x of z over here. If you multiply it with 1 minus 1 by 4 z inverse, this will get cancelled. So we have 3 minus 5 by 6 z inverse divided by 1 minus 1 by 3 z inverse. Z is 1 by 4, so z inverse will be 4. If you substitute it with 4, you will get 1. So A is equal to 1. We also need B. B will be limit z tends to the pole corresponding to B is 1 by 3. 1 minus 1 by 3 z inverse multiplied by x of z. We have x of z here. If you multiply it with 1 minus 1 by 3 z inverse, this term will get cancelled. So we get limit z tends to 1 by 3. 3 minus 5 by 6 z inverse divided by 1 minus 1 by 4 z inverse. Here z is 1 by 3, so z inverse will be 3. If you substitute z inverse by 3, you will get 2. So the value of B is 2. Now let us write x of z will be 1 by 1 minus 1 by 4 z inverse plus 2 multiplied by 1 by 1 minus 1 by 3 z inverse. ROC is not given in the question, but it is given that this is unilateral Z transform, which means ROC is always going to be the exterior of the circle outside the outermost pole. Here we have two poles. One is at 1 by 4, the other is at 1 by 3. So the outermost pole is 1 by 3, which means magnitude of Z should be greater than 1 by 3. From this we can write the sequence x of n. It is the inverse Z transform of x of z. The first term is 1 by 1 minus 1 by 4 z inverse. This is of the form 1 by 1 minus a z inverse, and it is right sided. So its inverse is going to be a raised to n u of n. Here a is 1 by 4, so 1 by 4 raised to the power n multiplied by u of n plus 2 times we have 1 by 1 minus 1 by 3 z inverse. This is of the same form, but a is 1 by 3. So its inverse is 1 by 3 raised to the power n multiplied by u of n. In the last video, we learned so many properties of bilateral Z transform. Most of them are the same for unilateral Z transform also. But there are some properties that are a little bit different. The first one is the convolution property. Assume we have a sequence x of n, its unilateral Z transform is x of z, ROC is R1. We have another sequence h of n, its unilateral Z transform is h of z and ROC is R2. Then according to this property, unilateral Z transform of the convolution of x of n and h of n is the product of x of z and h of z. Its ROC will contain the intersection of R1 and R2. But this is exactly the same as what happened in bilateral Z transform. What is the difference? The difference is there is a condition. Here, x of n and h of n should be 0 for n less than 0. This is the basic condition for unilateral Z transform. X of n and h of n both should be causal sequences. If you take h of n as the impulse function of an LTI system, then that LTI system should be causal. The next property we have to learn is time delay, which is time shifting but towards the right side. Assume we have a signal x of n, its unilateral Z transform is x of z. Then according to this property, unilateral Z transform of x of n minus 1 is going to be Z inverse multiplied by x of z plus x of minus 1. Let us try to prove this. We'll take a causal signal x of n. Since it is causal, it is going to be 0 for every value of n that is less than 0. So x of n will be a set of x of 0, x of 1, x of 2, and many terms like that. We know x of z is given as summation from n equals 0 to infinity x of n z raised to minus n. So here we can write x of z is going to be, if you give n equal to 0, just x of 0 z raised to 0 plus if you give n equal to 1, x of 1 z raised to minus 1 plus x of 2 z raised to minus 2. It goes on like that. Now let us take the shifted version of x of n, that is x of n minus 1. Assume this is x of n, then this will be x of n minus 1. X of n minus 1 is x of n shifted 1 units towards the right. Now, for unilateral Z transform, we only take values of n that is greater than or equal to 0. So for x of n, we'll be taking all of these values. This is x of 0, this is x of 1, this is x of 2, etc. For x of n minus 1, we will be taking all of these, where n is greater than or equal to 0. But for x of n minus 1 at n equal to 0, what we actually have is x of minus 1. At n equal to 1, we have x of 0. At n equal to 2, we have x of 1. So, if for x of n, we are taking x of 0, x of 1, x of 2, etc. For x of n minus 1, we are technically taking x of minus 1, x of 0, x of 1, etc. Or simply thinking, we have x of n minus 1. Since this is unilateral Z transform, n is only allowed to take values from 0 to infinity. If you give n equal to 0, this becomes x of minus 1. So the first term in this set is going to be x of minus 1. If you give n equal to 1, you get x of 0. If you give n equal to 2, you get x of 1. It goes on like that. We may have infinite terms. The 0th term will be this. Let's call this y of n so that we can call its Z transform y of z. Mathematically, we can write y of z is summation from n equals 0 to infinity x of n minus 1 z raised to minus n. If you give n equal to 0, you get x of minus 1 z raised to 0 plus you get x of 0 z raised to minus 1 plus x of 1 z raised to minus 2 plus it goes on like that. We have x of z over here. I want z inverse multiplied by x of z. So x of 0 will become x of 0 z inverse. X of 1 z inverse will become x of 1 z raised to minus 2. So we get this. But this is exactly what we have over here. Except there is one more term, that is x of minus 1. So we can write y of z is x of minus 1 plus z inverse x of z. And this is exactly what we have over here. Bilateral Z transform of x of n minus 1 is simply z inverse x of z, but here it is z inverse x of z plus x of minus 1. We are also considering the initial condition. Let's put x of minus 1 over here. We got the unilateral Z transform of x of n minus 1. It is z inverse x of z plus x of minus 1. Do you think we can write the unilateral Z transform of x of n minus 2 simply by inspection? For x of n minus 1, we had z inverse x of z. So for x of n minus 2, we'll have to start at z raised to minus 2 x of z. The next term will be z raised to minus 1 x of minus 1. There will be one more term, z raised to 0 x of minus 2. Z raised to 0 is 1, so let us remove it. This is the Z transform, so it is wrong to write equal sign. Let's replace it with a double-sided arrow. Now, do you think we can write the Z transform of x of n minus 3 in a similar way? We will start with z raised to minus 3 x of z plus z raised to minus 2 x of minus 1 plus z raised to minus 1 x of minus 2 plus z raised to 0 x of minus 3. Z raised to 0 is 1. Let us remove it. I hope you get the drill. One question I have is, why are we stopping at x of minus 2 and x of minus 3? It is not x of minus 2 and x of minus 3 where we are stopping. We are stopping at power of z being 0. Why are we not taking the further powers of z? Because the next power is going to be z raised to 1. After that, we will get z raised to 2. These are positive powers of z. In unilateral Z transform, we do not take positive powers for Z. So we have to stop wherever the power of Z becomes 0. Let us see the next property. It is first difference. Assume we have a sequence x of n. Its unilateral Z transform is x of z. Then according to this property, the unilateral Z transform of x of n minus x of n minus 1 is 1 minus Z inverse multiplied by x of z plus x of minus 1. The proof of this is pretty simple. Unilateral Z transform of x of n is x of z, and that of x of n minus 1 is z inverse x of z plus x of minus 1. So if we take x of n minus x of n minus 1 using linearity property, we get x of z minus z inverse x of z minus x of minus 1. X of z minus z inverse x of z can be written as 1 minus z inverse multiplied by x of z. And this is exactly what we have over here. Let's see the next property. It is time advance. This is again time shifting, but the shifting is towards the left side. Assume we have a signal x of n. Its unilateral Z transform is x of z. Then according to this property, unilateral Z transform of x of n plus 1 is going to be z x of z minus x of 0. Let us try to prove this. First, let's take x of n. Assume x of n is 0 for every value of n that is less than 0 because we are dealing with unilateral Z transform. So x of n will be the set of x of 0, x of 1, x of 2, etc. So its unilateral Z transform x of z will be x of 0 z raised to 0 plus x of 1 z raised to minus 1 plus x of 2 z raised to minus 2 plus it goes on like that. We want x of n plus 1, which is a shifted version of x of n. The shift is towards the left. So now we will be taking the terms x of 1, x of 2, x of 3, etc. It starts at x of 1 because for unilateral Z transform, we only take values of n from 0 to infinity. So if you take the first value 0, x of 0 plus 1 becomes x of 1. So the first term of x of n plus 1 is x of 1. Let's call it y of n so that we can call its Z transform y of z. Y of z will be the 0th term multiplied by z raised to 0 plus first term multiplied by z raised to minus 1 plus second term multiplied by z raised to minus 2 plus it goes on like that. We have x of z over here. I want z x of z. Then x of 0 will become z x of 0. X of 1 z inverse will become x of 1. X of 2 z raised to minus 2 will become x of 2 z raised to minus 1. So z multiplied by x of z will give us z x of 0 plus x of 1 plus x of 2 z inverse plus the next term will be x of 3 z raised to minus 2. It goes on like that. Now this is exactly what we have over here. Except here we have an extra term. So we can write y of z is actually zx of z without the zx of 0 term. So the unilateral Z transform of x of n plus 1 is zx of z minus zx of 0. This is what we have written over here. Again, let us try if we can find the unilateral Z transform of x of n plus 2 by inspection. Here we started with zx of z. So here we will be starting with z square x of z. Here we have minus zx of 0. So here we'll have minus z square x of 0. We won't stop there. We'll have one more term, minus zx of 1. Let's try to do the same for x of n plus 3. Here we'll start with z cube x of z minus z cube x of 0 minus z square x of 1 minus z x of 2. I hope you get the drill. Try to write the unilateral Z transform of x of n plus 4 by yourself. Let us solve a problem based on this. A causal LTI system is defined by the difference equation y of n plus 3y of n minus 1 is equal to x of n. Here x of n is alpha u of n and y of minus 1 is beta. We have to find out y of n, which is the output of the system. Here the system is causal and the input is also causal, because it is alpha multiplied by u of n. U of n is causal, so alpha multiplied by u of n is also causal. So here we can use unilateral Z transform. On the left hand side we have y of n, so we can write y of z plus, for 3y of n minus 1 we can write 3 times z inverse y of z plus y of minus 1. On the right hand side we have x of n, so we can write x of z. Now this becomes y of z plus 3z inverse y of z plus y of minus 1 is given in the question, it is beta. So 3 beta is equal to x of z, but x of n is alpha u of n. So x of z will be alpha multiplied by Z transform of u of n, which is 1 by 1 minus Z inverse. So we can write alpha divided by 1 minus Z inverse. Now here we have y of z plus 3z inverse y of z. Let us combine them and write y of z multiplied by 1 plus 3z inverse. There is a plus 3 beta here. Let's take it to the other side. It will become minus 3 beta. Now from here we can write an expression for y of z. For that we have to take 1 plus 3z inverse to the right hand side. Then we get alpha divided by 1 plus 3z inverse multiplied by 1 minus z inverse minus 3 beta divided by 1 plus 3z inverse. This is the Z transform of the output of the LTI system given in the question. Let's take the case where the initial condition is 0. That is, y of minus 1 is 0, which means beta is 0. If beta is 0, then this whole term will disappear in y of z. Y of z will simply become alpha divided by 1 plus 3z inverse multiplied by 1 minus z inverse. This is the output of the system when the initial condition is 0. We call this the zero state response. Now let us take the condition where input is 0. Input here is alpha u of n. If it is 0, that means alpha is 0. If alpha is 0, this whole term will disappear in y of z. Then y of z will become minus 3 beta divided by 1 plus 3z inverse. This is the output of the system when the input is 0. This is called the zero input response. The question is to find y of n. This is the output in the time domain. It depends on the values of alpha and beta. So as an example, let us take alpha to be 8 and beta to be 1. Substituting alpha and beta, this is what we get as y of z. Here we have 8 divided by 1 plus 3 z inverse multiplied by 1 minus z inverse. We'll have to apply partial fraction expansion there. We have to write it in the form a by 1 plus 3 z inverse plus b by 1 minus z inverse. First, let's find a. A is limit z tends to, the pole corresponding to a is minus 3. So z tends to minus 3. 1 plus 3z inverse multiplied by this whole thing, I'll just call it x of z. If you multiply this with 1 plus 3z inverse, this term will get cancelled. So what we have to find is limit z tends to minus 3, 8 divided by 1 minus z inverse. If you give z equals minus 3, this becomes 8 divided by 1 plus 1 by 3, which is 6. So we can replace a over here by 6. Now to find b, we have to take limit z tends to, the pole corresponding to b is 1. So z tends to 1. 1 minus z inverse multiplied by x of z. X of z is this whole thing. If you multiply it with 1 minus z inverse, this term will be cancelled. So what we have to find out is limit z tends to 1, 8 divided by 1 plus 3 z inverse. Z is 1, so this is actually 8 by 1 plus 3, which is 2. So we can replace b over here by 2. Now in y of z, we can replace this by these two. If we do that, y of z becomes like this. Two of these have the same denominator, so we can add them. 6 by 1 plus 3z inverse minus 3 by 1 plus 3z inverse will become 3 by 1 plus 3z inverse. Now let us find y of n by taking the inverse Z transform. Since we have used unilateral Z transform, we can assume that the sequence is going to be right-sided. The first term is 2 divided by 1 minus Z inverse. So it is 2 multiplied by inverse of 1 by 1 minus Z inverse if it is right-sided. It is u of n. Plus 3 multiplied by inverse of 1 by 1 plus 3z inverse. 1 by 1 plus 3z inverse is of the form 1 by 1 minus az inverse, whose z transform is a raised to n u of n, given that it is right-sided. Here we have plus 3, so a will be minus 3. Therefore, its inverse will be minus 3 raised to n u of n. Or together we can write y of n is 2 plus 3 minus 3 raised to n multiplied by u of n. Now let us bring back the initial value theorem and the final value theorem because they actually apply to unilateral Z transform. According to the initial value theorem, if x of n is equal to 0 for all n less than 0, that is if x of n is causal, then x of 0 is limit z tends to infinity x of z. And according to the final value theorem, if x of n is 0 for n less than 0, that is if x of n is causal, then x of infinity is limit z tends to 1, z minus 1 multiplied by x of z. We have already proven both of them in the previous video. So let us solve a problem. We have to find the initial and final values of x of n. Its unilateral Z transform is given. X of z is 0.5 z square divided by z minus 1 multiplied by z minus 0.5. Using initial value theorem, we know x of 0 is limit z tends to infinity x of z. That is limit z tends to infinity 0.5 z square divided by z minus 1 multiplied by z minus 0.5. Let's divide the numerator and the denominator by z square. Then we get limit z tends to infinity 0.5 z square divided by z square is 0.5 divided by, in the denominator, let us give one z to z minus 1 and the other z to z minus 0.5. So z minus 1 divided by z will give us 1 minus 1 by z multiplied by z minus 0.5 divided by z will give us 1 minus 0.5 divided by z. Here z is taking a very large value. So 1 by z will become 0. 0.5 by z will also become 0. So what we have here is 0.5. X of 0 or the initial value of x of n is 0.5. Again, according to final value theorem, x of infinity is limit z tends to 1, z minus 1 multiplied by x of z. So it will become limit z tends to 1, z minus 1 multiplied by 0.5 z square divided by z minus 1 multiplied by z minus 0.5. Here z minus 1 and z minus 1 will get cancelled. So it becomes limit z tends to 1, 0.5 z square divided by z minus 0.5. Now z takes the value 1, z square becomes 1, z over here also becomes 1. So this is equal to 0.5 divided by 1 minus 0.5, which is equal to 1. So the final value of x of n or x of infinity is 1. That's all about it for today. See you in the next video. And don't forget to subscribe.